Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Okay, here's the part B of section 8.5. Now in part A, we discussed various different types of disk block allocations. We talked about the contiguous allocations. We also talked about the linked allocation and the clustered allocation. We also mentioned that the linked allocation was very flexible because a user can store a file in various different parts of the disk space. Now here, we're going to provide the actual implementation for the linked allocation. Okay, now before we do this, let's recall an example in part A. Okay, so in part A, we just talk about example of a linked allocation. Now in this example, we have a file which occupied 4 disk blocks. Okay, so I hope we still remember. If you remember, the first block was 14, and then the next one was 17, and then block 3 and block 9. Now 14 was the first block. Okay, now the block 14 actually points to 17, and the 17 points to 3, and block 3 points to block 9. Okay, now let's color this. Okay, so the file occupies these 4 actually disk blocks. Now, the information of the first block is stored in the file control block. In this case, it's 14. Of course, the file control block contains other information attributes such as the length of the files and the protection information of the file and other information. Okay, so the first block is 14. It's pointing to 14. Okay, that was the example we just discussed. So now the diagram in this example seems to indicate that when we use the linked allocation, each block needs to provide the link information for the next block, right? So for example, 14, you need to provide the link information for the next block, which is 17. Okay. Now, the actual implementation in most of the operating system do not use this idea. Okay. They don't actually put the link information in the disk block. Okay. Rather than maintaining links as part of each disk block, they actually use something else. They mostly segregate the links in the dedicated area on the disk. So in this particular example, we use file allocation table. We call it FAT. Okay. Now FAT is an array where each entry corresponds to a disk block. Okay. So each entry 0, 1, 2, 3, they correspond to the disk block. Okay, and also the FAT keeps track of which disk blocks belongs to which file. Okay, so let's say for this particular file, now this 3, okay, belongs to the file, and 9 also belongs to the file. 14, 17, these belongs to the file. Okay. Now, FAT actually provide the link information by doing this. There's a second column next to each of the indexes. Okay, this actually provide the next block, after these block number. For example, the 14, if the current block is 14, so the next block 14.2 is 17. So we're gonna put the 17 information of 17 in these FAT. Okay, and then this way you link the block 14 to disk block 17. And the 17 points to 3, so you're going to provide the information 3 in here. And this actually maps 17 to 3. And then 3 points to 9, so this maps to 9, and 9 points to nowhere, because 9 is last block. Okay. Now, for a file that related to this file control block, now instead of actually pointing 14 directly to the the actual file control, actually disk blocks, then you actually point this to the index 14 in the FAT table. Okay, so we're not going to use this anymore. We're not going to use the link over here. We're not going to use the actual link between the disk blocks, but we actually provide a link using the FAT table. Okay, using the FAT. Now, using FAT is very, very good because both sequential and direct access is accomplished efficiently by following the link in the FAT. Okay, instead of working between the disk block, you're going to work just between the indices. Okay, in the FAT table. Okay, so also the file can easily be expanded by allocating new block. For example, if the file, we want to expand the file from 4 actually disk blocks to 5. Okay, so first we need to find a free block, right? So we find a 2. Okay, 2 is free. Okay, so then what we do is we're going to update the FAT. Okay, so here, so instead of 9 points nowhere, we're going to point 9 to 2. Okay, now this way you basically point 9 to 2, right? And then 2, the block 2 becomes the last block, so you're going to point to nowhere. We use dash. Okay, so we just added an additional block for the file, and it's just actually update the numbers in the FAT. So this way we can easily expand the file. Okay, so the FAT provides all the advantages of a linked allocation, including the ability to easily expand a file. Okay, now since the FAT resides in a small number of designated disk blocks, the blocks can be cached in main memory. So consequently, so here the sequential access is more efficient. Okay, since no seek operations are necessary to follow the pointers. So instead of using pointers, we use the index table. Okay. Now direct access is also possible because the location of the desired block can be found efficiently by scanning the chains of indexes in the FAT. Okay. So the FAT allocation has a lot of advantages. Okay. So that's the reason why we don't implement the links information in the disk block. Instead, we use a dedicated table called a FAT. Now, another implementation for the disk allocation is the indexed allocation. Now, with an indexed block allocation scheme, file blocks may reside anywhere on the disk, and the index table is provided for each file, which keeps track of the blocks belonging to the file. Okay, so let's take a look at the same examples we used before. Okay, suppose I have a file which used a couple of disk blocks. The first block was 14, second block is 17, and 3 and 9, right? We use that example. And 14 is the first disk block. Now, using the index allocation, there's an index table. Okay. Now, the index table contains a number of indexes, 0, 1, 2, 3, 4. Now, how big is the index table depends on the size of the file you want to use. Okay. So at this moment, if the index table, contains more than 4, that should be enough, right? Because the file only use 4 disk blocks. Okay. Now each index is associated with the disk blocks. 0, the first block is 14, so the index 0 is going to point to 14. And the second one is 17, is point to 17. And then the third one, number index 2, points to 3. And then the fourth one, index 3, points to 9. Okay. Now, for the file control block, we just need to provide the link to the index table itself, right? So that's the index table. Of course, there are some other attributes, but the file control blocks contains the information about the index table, so point to the index table. Now, indexed allocation is very easy to extend. For example, if the file is currently using 4 blocks, disk blocks, if the file wants to expand to 5 blocks, so we just need to check which block is available in the disk space and then update the index table. For example, we want to expand to one more block 0, okay? Now all we need to do is expand it, if the table can, for the next index 4, the 5th index, we're going to put the 0 information and the point to 0. Okay, so it's pretty simple, right? Now, an indexed allocation has many advantages. So the main advantages are: 1, fast sequential as well as direct access. 2, ability to efficiently expand a file by simply adding new block numbers to the index table. So it's easy to expand. Okay. Now, here's the main drawback. Okay. A simple indexed allocation has a main drawback. So that is the necessity to decide a prior how big the index table should be. Okay. Because once you allocate the index table, it's fixed. So if the file expand, then the expansion has a limit. You cannot expand the file to the size which is more than the index table can accommodate. So a small table limits the maximum size of file. A large index table wastes disk space, since most of the file will have no need for large size. So let's talk about some of the variation of the simple index allocation. Okay. So one of the variations of the simple indexed allocation pioneered by the Unix operating system is an index table that can expand as necessary. Now, in this approach, an expanding index allocation maintains the numbers of the first 10 blocks directly in the file control block. So in this, implementation, the file control block contains the first 5 blocks. File block 0, file blocks 1, all the way to file block 9. Now, the advantage of this implementation is that the small files completely avoid the penalty of accessing an index table. Okay. So in this case, if the file size is smaller than 10 file blocks, then everything can be handled in the file control block, right? Now, what about if the file size is bigger than 10? So then the next 128 file blocks are recorded in a one-level index block. Okay, so then the next point is not point to the 5 blocks, but it's point to a one-level index. Okay, starting from the 5 block, the numbers for the 5 block 10, and all the way to 5 block 137, right? Because the size of this one level index block is 128, but it's starting from 10, so it's end at 137. So if the file size is 138 or less, then accessing the file information can be done either in the file control block or one level index block. Okay. Now, if the file exceeds 138 blocks, so then we need to create an additional two-level index table. Okay. Two-level index structure. Okay. Now, the first level index block points to 128. There's 128. The second level index blocks for a total of, it's 120 times 120, which gives you 16,384 blocks. Okay, so that's the two-level index. That's the one-level index. Okay. Now, the two-level index is going to start from the file block 138, all the way to 16,384. Okay, let's say, 521. Sorry, because it's actually start from 138. 138 plus the number of blocks, which is 16,384. So that's 16,521. Okay. Okay. So if the file size is smaller than 16,522, then the file access can be controlled within the file control block and the 1-level index block and the 2-level index block. Okay. Now, if the file size is bigger, okay, then the same principles can expand the file further by 3-level index structure. Now, 3-level index structure can record additional 128 times 128 times 108, which can actually add additional of more than 2 million additional blocks. Okay, that's a huge number. Okay, that's one of the variation for the simple indexed allocation. Now, there's various different ways to manage the free disk space. Now, one of the simplest approach is called bitmap. So a bitmap is a data structure where each bit represents one disk block. So if the disk space contains, for example, 1 million blocks, then you need to maintain a bitmap of 1 million bits. Okay, so each bit represents one block. Okay, now whether a block is free or occupied is represented by the value in the bitmap. For example, here, block number 0, the first block is occupied, second block is occupied, block 10 is occupied, 11 is occupied, and 12 is occupied, right? So in the bitmap, we have a corresponding, okay, bit. Each bit, represent a block. The first bit represent block 0, second bit represent block 1, and that's block 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, 10 has the value 1, so that means block 10 is occupied, and 11 is 1, 12 is 1, and 13 is 0, so that means 13 is free, right? So we can continue to do that. Okay, so this is a very simple concept, and the bitmap use minimum number of space to manage the free space. Thank you.